Hello, everyone. Thanks for joining this session. The topic today is real-time data platform from Lakehouse to Streamhouse. So in this session, we will share some open research on real-time data platform and explore the latest technologies and architectures like Streamhouse. It does not represent any in-house projects at LY Corporation. So before we dive in, let me quickly introduce myself. My name is Xiao Zhiyan. I'm from Chongqing, China, which is also known as the 8D Magic City. I graduated from the Chinese University of Hong Kong, majored in mathematics and information engineering. I'm currently working as a software engineer at LY Corporation, focusing on data pipeline side. I'm interested in improving big data systems with Rust. So if you are also interested, welcome to join our open data-driven community to explore technologies like Streamhouse, AI native, Rust, and more. So the topic today is a real-time data platform. But why this topic and why now? Because we are experiencing a large shift happening around us. We used to say that software is eating the world. Every business became a software company. Then came AI, and AI started eating software. But now, real-time is eating everything else. We expect instant responses like live dashboards, real-time alerts, on-the-fly personalization, and even instant feedback from AI agents. But the truth is, most data platforms do not fully support real-time scenarios. So we need a real-time data platform, and the Streamhouse is a promising design of it. First, let's have a look at the early days of data platforms. In the beginning, we had a data warehouse, which is a powerful system to ingest the structured data through ETL process and then provide SQL access for downstream users to create a BI or reports. But it doesn't support semi-structured or unstructured data very well. Then we had a data lake architecture to store such data on distributed storage like HDFS or AWS S3. To properly query from a data lake storage, we need to use some query engine like Spark, which not only supports previous BI or reports, but also enables machine learning on various data sources. When we compare data warehouse and data lake, we can see that data lake can support more data types and easier scalability at a lower cost. However, it doesn't support transactions, and the overall query performance is lower than that of data warehouse. So can we combine the advantages of both systems into one? Yes, then we get a Lakehouse. And its name is actually a combination of data lake and a data warehouse. So here is the data lake architecture from previous page. Then how to turn it into Lakehouse? We just need to add an extra layer called Lakehouse table format, like Apache Iceberg. The key point of Lakehouse table format is to index data files with stats to speed up queries. Popular table formats include Apache Iceberg, Delta Lake, and Apache Hudi. They support transactions and have higher query performance. However, when we try to build a real-time data platform using Lakehouse, there are still some problems. The data pipelines can have latency of 5 to 30 minutes, and the throughput of streaming write is not that high. Then, how to support low latency streaming processing? We can just add an extra streaming pipeline in addition to previous batch pipeline. Then we get Lambda architecture. Here is a simplified batch pipeline. We can use Spark to ingest the data from data sources and save it to Lakehouse storage like Iceberg. Then data users can access the data through query engine. Then we just create a separate streaming pipeline with Flink to ingest the latest data and save it to streaming storage like Kafka in real time. So the key point of Lambda architecture is the dual layer design for batch and streaming pipelines. This design enables streaming processing with sub-second latency. However, the complex architecture leads to high development and operational costs. If we want to integrate real-time and historical data, we need to merge the results in both layers. But historical data inherits the latency of Lakehouse and is not real-time. How can we improve this design? Is it feasible to unify these two data pipelines? Yes, then we get a Kappa architecture. There is only one streaming pipeline to ingest the data from Kafka sources and save it to streaming storage like Kafka in real time. The key point is to treat all data as streams without introducing additional batch pipeline. If we want to manage historic data, we need to replay all streams. As we can see, this simple architecture can support sub-second latency, but long-term storage for replaying historic data is quite expensive. And the streaming storage, like Kafka, is inefficient for ad hoc queries or complex analytics. Considering these drawbacks, can we improve Kappa architecture with Lakehouse storage? First, let's have a look at the data pipeline from previous Kappa architecture. The unified data pipeline can achieve sub-second latency with Kafka. Then we introduce Lakehouse as tiered storage to replay historical data at a lower cost. If we directly access the tiered storage from query engine, the query performance should also be improved. However, the historic data would have significant latency, as we have seen in Lakehouse before. Is it possible to improve it? Yes, we can adopt some streaming-first Lakehouse storage, like Apache Pymon. It has features of Lakehouse, but is designed to be streaming first. Thus, it can achieve sub-minute latency and perform better than Iceberg for streaming processing, although it's still not as fast as Kafka. But if sub-minute latency is acceptable, we can get a unified, near real-time pipeline by replacing Kafka with Pymon. So how does Pymon support both streaming and Lakehouse features? Let's look at some details about Pymon, a streaming-first Lakehouse table format. Here is a file layout of Pymon from its official website. On the left are metadata files such as snapshot, schema, and manifest. On the right are data files organized by partition and bucket. So metadata is managed hierarchically through snapshot, manifest list, and the manifest file. And the data files are indexed with stats, similar to other Lakehouse table formats like Iceberg. Therefore, Pymon has Lakehouse features like predicate pushdown to support efficient queries. So why is Pymon a streaming-first format? It supports streaming write to multiple buckets in parallel to achieve higher throughput. It also supports changelog of primary key tables and streaming read for appended tables. Therefore, Pymon, as a Lakehouse table format, can also be used similarly to Kafka, but with sub-minute latency. So can we further improve unified pipeline to achieve sub-second latency? First, let's have a look at the near real-time pipeline we talked about earlier. We replaced the streaming storage Kafka with Lakehouse storage Pymon to achieve better query performance at the expense of sub-minute latency. What if there was a streaming storage with much better query performance than Kafka? Well, there is. That is Fluss, a streaming storage for real-time analytics. Let's add Fluss to the pipeline and use Pymon as its tiered storage. Just similar to Kafka mentioned before, then we can achieve sub-second latency as well as good query performance with the Fluss. If we query historical data offloaded to Pymon, it's still close to real time with just a sub-minute latency. Let's compare Fluss to Kafka and see why it wins. Kafka stores row-based data records in binary format, while Flask stores records in column-based arrow format. And Kafka relies on external registry to manage schemas, while Flask manages schemas internally. So Flask supports advanced query features like projection pushdown, which Kafka does not. In addition, Flask uses Arrowflight as a query interface, which has much higher performance than Kafka Consumer or REST API. Now, with Pymon and Flask, we can call it unified real-time pipeline. Now let's summarize what we have discussed so far. We first introduced the data warehouse and the data lake. Then we combined them to form Lakehouse. To support streaming processing, we introduced the Lambda architecture and unified it with Kappa architecture. Later, we tried to improve Kappa with Lakehouse storage. After adopting Pymon and Flask, we got unified real-time pipeline. We call this architecture Streamhouse. Streamhouse is also called a streaming lakehouse, which is actually a lakehouse with streaming capabilities. The key point of it is to use Pymon to achieve unified data pipeline with sub-minute latency. And we further improve it with Flask to achieve sub-second latency. So now we've got our real-time data platform in the name of Streamhouse. Now we have seen the latest Streamhouse architecture with Pymon and Flask. Are there any other potential improvements as a real-time data platform? Let's imagine how we might orchestrate data pipelines. We need to create and deploy the Flink jobs manually. If we need to update them, we need to make the code change and redeploy. So when we want to create new pipelines, we will just repeat this process with some separate code base. All this process is not really automated or even autonomous. So let's think about how to improve it. What if we change these static data pipelines to some lively composable data flows? Here are some typical data pipelines with corresponding data layers. First, we ingest from data sources and save raw data in ODS layer. Then we clean the raw data and save it in a DWD layer as a basis for subsequent processing. To speed up repeated queries, we aggregate some data and save it to DWS layer. In addition, we can customize some data for specific applications and save it to ADS layer. We can implement all these pipelines in Streamhouse architecture. For creating and orchestrating pipelines, is it possible to fully automate this process? Let's treat each pipeline here as a reusable data action defined by SQL. Then we create a data flow in YAML file to include required data actions. Next, register the data flow and the data actions in a central registry so that others with appropriate permissions can access them. To execute the data flows, we need a flow materializer to fill in required parameters and adapt it to a runtime like Flink. Additionally, we can create a flow trigger to execute selected data flows when certain conditions are met. With this design, we can reuse existing data flows to create our own data flows. We can reuse existing data actions to create our own data flows, or even reuse existing data flows when feasible. And the execution of data flows can be automated and able to adapt to changes when some conditions happen. So we call this dynamic data flow. If we can implement automated data flow, can we move one step further to support autonomous data flow? Here are the components to support dynamic data flow from previous page. We can see flow trigger, data flow, data action, flow materializer, and the registry. Let's try to connect them with agentic AI, which is a system to orchestrate different AI agents autonomously. First, agentic AI might receive some information from some flow trigger. Then it can determine if any changes need to be made. If a data flow needs to be created or updated, the flow planner agent is instructed to search the registry for reusable data flows or data actions. If no suitable data action is found, Action Composer agent is instructed to create and register a new data action. When a new data flow is created and registered, Orchestrator agent is instructed to call flow materializer and execute it using the corresponding runtime. So with this agentic AI, we can also create data flows with user prompt using natural language. We call it AI native control plane of Streamhouse. Now let's recap. We introduced unified real-time data pipeline as the core of Streamhouse. Then we discussed dynamic data flow. Building on this, we thought about AI native control plane. So what do you get if you combine them all? We call it the AI native Streamhouse. We look forward to it becoming the next generation real-time data platform. It not only supports real-time pipeline execution, but also autonomous pipeline orchestration. We have just discussed the way to build a real-time data platform from Lakehouse to Streamhouse and even AI-native Streamhouse. But the Streamhouse architecture is still quite new. Let's see how it can bring real value to our business. Then we can explore, build, and share Streamhouse implementations together. So here are some links to the core concepts of today's session. If you're interested in the details, you can check these links. Yep, so that's a sharing from me today. Thank you.